In this video, we are going to look at the resistance of 5 different electrical components, and we're going to look at the resistance primarily by looking at their current potential difference characteristics. So we're going to start by describing Ohm's law in words and also looking at a graph of a component that shows Ohm's law. We are going to describe how the resistance of 4 non-ohmic conductors changes with various external stimuli. And then finally, we will describe an experimental procedure to investigate the current potential difference characteristics of any electrical component. For this, all you are going to need is a pen and paper or your science book in front of you so that you can answer a few checkpoint questions along the way. So today we are going to look at 5 different electrical components. We're going to be looking at resistors and variable resistors. We're going to be looking at lamps, sometimes also called filament bulbs, diodes, thermistors, and light-dependent resistors. So let's start with the resistor or the variable resistor. These are both examples of ohmic conductors. This is because they obey Ohm's law. Ohm's law states that the current through a component is directly proportional to the potential difference across it, providing the physical conditions are constant. I'm going to repeat that one more time. Ohm's law states that the current through a component is directly proportional to the potential difference across it, providing the physical conditions are constant. And when we say physical conditions, we mean, for example, that the temperature has to stay the same. If the current through and the potential difference across are directly proportional, it means that as the potential difference increases, the current increases by the same factor. If we double the potential difference, we double the current. So, what does this look like on a graph? If we were to plot a graph with current on the y-axis, and remember we use the symbol I for current, and potential difference on the x-axis, and remember we use the symbol V for potential difference. If you have an ohmic conductor, for example a resistor or a variable resistor, then we get a straight line graph through the origin. So we can see here that we have got a straight line with a constant gradient. If we were to plot the potential difference on the y and the current on the x, we would also get a straight line graph through the origin. And importantly, you should be able to see that if we look in the negative direction, so we reverse the direction of the current in both of them, we have a symmetry between the forwards and the backwards direction. This means it doesn't matter which way around you plug in your resistor or your variable resistor, it will always obey Ohm's law, whether the current is going forwards or backwards. Crucially, because the current and the potential difference are proportional, the resistance of an ohmic conductor is constant. So for a resistor or a variable resistor, if you put it in a fixed setting, providing you do not change the temperature, the resistance will be constant. So let's now look at these graphs in more detail. If you have a graph of potential difference against current, the gradient is equal to the resistance. So that means if you measure the change in y, which is our potential difference, divided by our change in x, which is our current, then you can find out the value for the resistance. If you have got the graph the other way around, so this graph on the left-hand side here, then the gradient is equal to 1 over the resistance. So you'd have to calculate the gradient first, and then you would do 1 divided by the gradient to find out the resistance. So let's now look at just one of these graphs in more detail. If you've got a graph of potential difference on the y and current on the x, the gradient is equal to the resistance. So this line here representing a component we can see is quite shallow, the gradient's quite small. This means the resistance is low. This red line that I've just drawn could be for another resistor, and we can see here this is much steeper, the gradient is much larger, and therefore this is representing a component with higher resistance. So we are now going to do some checkpoint questions. So checkpoint question 1 is, what is Ohm's law? You have got 4 different options there. I'd like you to pause this video now, and then you are going to choose A, B, C or D. Good, so hopefully you have paused the video and you have selected one of these for Ohm's law. The correct answer should be A. The current through a component is directly proportional to the potential difference across it, providing the physical conditions are constant. Let's now have a look at another example. These are 2 graphs. You have got potential difference on the Y and you have got current on the X. You are now going to pause this video and you are going to decide which of these has the lower resistance, and you have been told that the gradient of these graphs is equal to the resistance. So pausing the video now and answering that question. So hopefully you have now got on your piece of paper an answer that says either A or B. Now in this one, because the gradient is equal to the resistance and we want a low resistance, you are looking for a small gradient, and that means it is the graph on the left-hand side, graph A, because this line is a lot less steep, it's got a shallower gradient. And checkpoint number 3, can you pause the video and answer this one? You have now got current on the Y and potential difference on the X, and the gradient is equal to 1 over the resistance. Good. So you should now have either A or B written down on your piece of paper. Now in this case, the gradient is 1 over the resistance, and we want the component with low resistance. Because the gradient is 1 divided by the resistance, it means to work out the resistance, we do 1 divided by the gradient. And when we divide by a big number, we get a small number. So in this case, we wanted a large gradient, and we can see that here we have got a steeper value than we have for the gradient on A. We have now looked at Ohm's law, and we've looked at 2 examples of components that obey Ohm's law, that is the resistor and the variable resistor. We are now going to look at our first of 4 non-ohmic conductors. And we are going to start with the lamp, which is in the pink box here, sometimes also referred to as a filament bulb. A filament is a very, very small metal wire. It is very narrow and very short. In any metal, or in a metal wire, there are atoms or ions of the metal itself. These are represented here by the gold circles. And we've also got a sea of free delocalized electrons, and they are represented here by the blue dots. It is these free delocalized electrons that are the charge carriers that move through our circuit. They provide the charge flow and therefore cause the current. In a filament bulb, as the potential difference increases, the temperature of the metal filament increases as well. If the temperature increases, then these ions start to gain more kinetic energy and they will start vibrating more. So they'll be vibrating with larger amplitude around their fixed position. Because they are vibrating more, it is harder for the electrons to pass through because it increases the frequency of collisions with the atoms. The electrons will physically collide into the atoms, making it harder for them to move through. And this means the current will be lower because the resistance has increased. This means that if we were to plot current against potential difference through a filament bulb, we can see that this is not an ohmic conductor. They are not directly proportional. So let's now talk through the different parts of this graph. The central part here, initially, as the potential difference increases, the current increases at a similar rate. It is very nearly directly proportional. And we can see that this is the same whether it is flowing in the forwards direction or the backwards direction. However, as the potential difference gets higher, and we know that this, as the potential difference gets higher, that temperature also gets higher, this means that the current does not increase as quickly because we know that those electrons are colliding more frequently with the atoms or the ions. And that is why we see this curve. We can see the potential difference is increasing much quicker than the current. And crucially, we see the same in both directions. And eventually, these lines will become completely flat because the current can no longer increase. And then that resistance is really, really high. So we're going to do a quick checkpoint on filament lamps. So you have got 3 multiple choice questions to answer here. Read them through nice and carefully. Make sure you pause this video whilst you answer the questions. So you should now have 3 answers on your page, 1 for question 1, 1 for question 2, and 1 for question 3. If you have not, then please pause again and make sure you answer all the questions. If you have, then stay on the line and we will go through these answers now. So, as the potential difference increases, the temperature increases. So we should have put A for question number 1. The charge carriers in the metal conductor are electrons. It is the free delocalized electrons that can move throughout the material. And then question number 3, the higher the temperature, the higher the kinetic energy of the ions. That is true. The larger the amplitude of the ion vibrations. That is also true. And the higher the kinetic energy and the larger the amplitude of vibrations. That is the most true of all of them because it takes into account both A and B. So the best answer here was C. So we have now looked at ohmic conductors. We have looked at a filament bulb or a lamp, and now we are going to look at the final 3 non-ohmic conductors, the diode, the thermistor, and the light-dependent resistor. So let us start with the diode. The diode is an unusual component in that it only lets current flow in one direction. So if you have a look at this graph, we can see that if the current is flowing in the negative direction, if the potential difference, is in the negative direction, the current is 0. No current can flow when the potential difference is in the negative direction. So backwards, the resistance is so high, it's essentially got infinite resistance, that the current is 0. However, in the forwards direction, initially the resistance is really high, so no current can flow. But after a threshold potential difference, suddenly the current increases really quickly. And this is almost an exponential trend of increase. It increases rapidly. So for this section of the graph, once we get the current flowing, the resistance is really, really low. Remember that on a current potential difference graph, 1 over the resistance is the gradient. That means the steeper the gradient, the lower the resistance. So diodes do not have a symmetrical current potential difference curve because the current can only flow in one direction. This circuit symbol here is for a light-dependent resistor, often just called an LDR. Now, a light-dependent resistor is one in which the resistance changes depending on the light intensity. If the light intensity is high, that means we've got lots of light shining on a component. If the light intensity is low, it means we have very little light shining on that component. So we can see here, as the light intensity increases, the resistance decreases. So as the light intensity increases, the resistance decreases. That means if it's really, really, really bright, the resistance is really low. And if it's dark, the resistance is high. This is particularly useful in 2 main applications. One is in things like street lamps. They can come on automatically when the light drops below a certain level. So you'll see at night time in the city, the street lamps come on. That is not because someone is individually pressing a switch, but because they have used a light-dependent resistor to help with that. You can also use it in security systems where you have, for example, lasers connecting different places together. And when that laser is broken, it means the light can't shine on the light-dependent resistor. And so suddenly the resistance will change really dramatically, and so we can detect that someone has entered. And then the final component is a thermistor. A thermistor is a resistor whose resistance changes depending on the temperature. It behaves very similarly to a light-dependent resistor, but its external stimulus is temperature instead of light. With a thermistor, as the temperature increases, the resistance decreases. So we can see here when we've got a high temperature, the resistance is low. And when we've got a low temperature, the resistance is really high. So as the temperature increases, the resistance decreases. This is very useful in thermostats to regulate heating. They can be set up so that the heating comes on or turns off when the temperature reaches a certain value. We have now got 3 questions, one on diodes, one on thermistors, and one on light-dependent resistors. Can you please pause this video and answer these 3 questions? You should now on your page have 3 answers, one for question 1, one for question 2, and one for question 3. So let's go through these now. So as the temperature increases, a thermistor's resistance will decrease. So we should have put C for question number 1. Number 2, as the light intensity increases, a light-dependent resistor decreases. So we should have put C for number 2 as well. And finally, number 3, the correct current potential difference graph for a diode. Well, the first one here, this is an ohmic conductor, so this could be a resistor or a variable resistor. This one here we should now recognise as the filament bulb, and then C is of course the diode, because we know that a diode is a component where the current can only flow in one direction. We have now gone through the variable resistor, the lamp, the diode, the thermistor, and the light-dependent resistor. So the final thing to do is to determine how is it that we've actually been able to look at the current potential difference relationships of any electrical component. And we can do that by using a circuit that looks like this. And I'm going to talk you through this circuit now. We always need to have a source of potential difference that enables current to flow through our circuit. That is provided here by the battery. We then need a way of changing the current in the circuit so that we can change the current through our component, and we do that with the variable resistor. So this is not the component being tested. We're using the variable resistor in order to change the current in the circuit. We need to be able to measure the current. We do that using an ammeter, which is always connected in series. And we need to be able to measure the potential difference, which we do using a voltmeter, which is always connected in parallel. And then this here is where we insert whichever electrical component we are interested in investigating. And in this case, we are looking at a lamp or a filament bulb. So what we would do is we would take a series of readings. We would initially set it up so that the current was 0, and we would take the reading on the ammeter and the voltmeter. We would then change the value on our variable resistor, which would change the current and therefore change the potential difference across our lamp, and we would write that into our table. You would do that for 6 different readings, and then crucially, if you remember that all our graphs had both a positive and negative direction, you would then have to change the direction of the source of potential difference. So I'll show that one more time. We did have this battery facing the other way around, and now we have turned it around, and then you can take 6 more readings. Now, if you want to work out the resistance from these, We have an option to plot a graph, and then we can look at how the current and potential difference change one another. And again, we can look at the gradient of that if we've got a straight line graph. We can also work out the resistance for each individual value by using this equation. The resistance is the potential difference divided by the current. So this is a setup that we would use to measure the resistance of any electrical component and how we can investigate the current and potential difference relationships. There will be no more information that is new in this video. We are now going to go through one model example to kind of show you the kinds of questions that you might be asked. So we're going to look at this question. A student wants to investigate how the current through a filament lamp affects its resistance. Use the circuit symbols in the boxes to draw a circuit diagram that she could use. So again, that is the experiment that we just looked at. It should look something like this, and there are a few crucial things where those 2 marks have come from. The first mark is to have the battery, the ammeter, the lamp, and the variable resistor all in series. And the second mark comes from having the voltmeter in parallel. And again, if this question was asking for something other than a filament lamp, you would just replace this component with whichever component you were investigating. And so the final question said, describe how the student could use her circuit to investigate how the current through the filament lamp affects its resistance. We always do a numbered method. So 1, set up the circuit as shown. 2, use the ammeter to measure the current. 3, use the voltmeter to measure the potential difference across the filament lamp. 4, change the resistance of the variable resistor to change the current in the circuit, and therefore change the potential difference across the filament lamp. 5, take at least 6 readings in the forward direction. 6, repeat the experiment with the direction of the current reversed. And finally, number 7, the resistance of the filament lamp can be calculated using resistance equals V over I, or you could say that you could plot a graph of current against potential difference and look at the gradient. Can you now turn to the rest of your homework? You have got your look, cover, write, check and your questions to answer.